Hello, this is Richard Collins with Part 2 of the Unit 4 lecture. Ice crystals create some of the most beautiful light displays in the atmosphere that are visible in Alaska. Light is scattered by ice crystals that are hexagonal plates and columns. Light enters the ice crystal and is reflected around the crystal and back out again. Thus, the light enters and exits the crystal at different angles. Furthermore, the crystal acts as a prism where different colors are refracted at different angles and thus are separated. For random-oriented hexagonal crystals, the crystals create halos around the sun and moon. The random orientation of the different crystals remixes the colors, so the halo appears white. For hexagonal plates falling horizontally, the color separation is preserved, and ice dogs appear as mini rainbows on each side of the sun. The appearance of a halo around the moon at night is used as a forecasting tool, as it indicates the presence of ice clouds and the coming change in weather. Ice clouds often travel ahead of storm systems. The classic optical display is the rainbow. Historically, the rainbow has been a meteorological feature of cultures around the world. Unlike the ice dogs, the rainbow is seen when the sun is behind the observer and there is rain in front of the observer. Colors are separated as they travel through the raindrops and reflected back to the observer. From each raindrop, the violet reflects high and the red reflects low. However, at the observer's eye, it is the combination of light from different raindrops that is seen. Red light comes from raindrops higher up than those the violet light comes from, and so the rainbow appears to have red on top and violet on the bottom. The sailor's warning includes an assumption about the predominant direction of the wind. Can you explain the meteorology behind the warning? Rainbow in morning, sailors take warning. Rainbow at night, a sailor's delight. The average temperature of the Earth is determined by the energy balance between the incoming solar radiation, which is visible, and the outgoing terrestrial radiation, which is infrared. In an atmosphere-free Earth with an albedo of 30%, the balance yields a global average temperature of about minus 18 degrees Celsius or 0 degrees Fahrenheit. An atmosphere with gases that absorb in the infrared, e.g. carbon dioxide, methane, and water vapor, is warmer. This is because the absorbing gases capture some of the infrared radiation emitted by the Earth and re-radiate some of that radiation back to the surface where it heats the Earth. Thus, in the example of an atmosphere with water vapor, the temperature of the Earth rises to plus 15 degrees Celsius or 59 degrees Fahrenheit. As we discussed in the opening slide, while the energy in and out of the Earth atmosphere is in balance over the year, the balance does not exist at each latitude. The global balance over the year means that the net energy gained or lost by the Earth atmosphere is constant, and the global temperature stays constant year to year. While the Earth loses infrared energy relatively evenly at all latitudes, the energy absorbed from the sun decreases with latitude as the sun is lower in the sky and the footprint of the sunbeams is larger and the energy is less concentrated. The energy deficit at the poles is amplified by the polar ice caps that increase the polar albedo and reduce the solar heating even further. The tilt of the Earth results in the seasons. As the northern hemisphere leans toward the sun in summer, the sun is higher in the sky and the sunbeams spread out less on the ground. The solar energy is more concentrated and the sun heats the ground more effectively. In winter, the sun is lower in the sky and the sunbeams spread out more on the ground and heat the ground less effectively. Furthermore, days are longer in summer than winter, and so in summer the ground is heated more strongly over a longer day than in winter. These two factors add together to make summer significantly warmer than winter. This difference is larger at the higher latitudes, and thus the seasonality is greater at the poles than the tropics. The variation of temperature through the day is also determined by the balance between incoming solar and outgoing terrestrial radiation. The idealized plot in the upper right shows the energy balance and resultant temperature over the course of the day. The coldest part of the day is just after sunrise, when the atmosphere has been cooling all night and the increase in solar heating begins to overcome the thermal cooling. Through the day, the solar heating increases more rapidly than the increase in cooling, and the maximum temperature is found in the late afternoon about 4 p.m. The meteogram from Austin, Texas in the lower left shows the general reproducibility of the diurnal cycle of temperature over 4 days. The temperature at the ground, or surface air temperature, is driven by the ground. In the daytime, the ground warms rapidly, and that energy is transferred into the adjacent atmosphere by conduction. Thus, the temperature is warmest at the surface, and this warming extends into the atmosphere through convection. At night, the ground cools, and energy from the lowest atmosphere is conducted into the ground. An inversion can occur where the air at the ground is colder than the air higher up. The formation of inversions during long winter nights in Fairbanks is critical to determining the quality of the air in Fairbanks in the winter. Clouds act to cool the ground in daytime by reflecting sunlight back to space that would otherwise reach the ground. Clouds act to warm the ground in nighttime when they absorb infrared radiation that is leaving for space and re-radiate some of that infrared radiation back to the Earth. Thus, by cooling during the day and warming during the night, clouds reduce the daily temperature range. This behavior is evident in the meteorological data from Texas, where there is a transition from clear skies on the 18th of February to cloudier conditions on the 19th of 20th February and a return to clearer conditions on the 21st of February. The daily maximum temperatures are higher during clear conditions and lower during cloudy conditions. The daily temperature range is higher during clear conditions and lower during cloudy conditions. Water is a unique substance. Molecules of water are electrically polarized so that the oxygen atom has a net negative charge and the hydrogen atoms have a net positive charge. Opposite charges attract, so the hydrogen atom in one molecule is drawn to the oxygen atom in another. Thus, water molecules stick together, and this is the reason water is a liquid at room temperature rather than a gas. This also means that water requires more energy than expected to be heated to pull the molecules apart and increase their kinetic energy. The specific heat capacity is the amount of energy it takes to raise the temperature of 1 gram of a substance by 1 degree Celsius. For water, it takes 4.2 joules of energy to do that. What is 4 joules? 4 joules represents the energy released when a mass of 1 kilogram falls about 40 centimeters onto your toe. In comparison, air and soil have much lower specific heat capacities. Air has a specific heat capacity of 1 joule per gram degree Celsius at 300 Kelvin and 1000 hectopascals, while that of soil is 0.8 joules per gram per degree Celsius. This sluggishness, scientifically called thermal inertia, is further increased by the fact that the surface water that is warmed mixes with colder water below. The sunlight is absorbed not just at the surface, but through some depth of water, and finally, some energy is lost to evaporation of the water. So, when it's all said and done, it takes a lot more energy to change the temperature of water than air or soil. So the temperature of the sea changes much less than land over the diurnal and annual cycles. During a sunny day, the beach is much warmer than the water. In coastal communities, winter temperatures are generally higher than the temperatures of communities further inland, and conversely, they are lower in the summer. In the 1970s, University of Alaska professor Glenn Shaw was intrigued by the fact that the air in Fairbanks was hazy in late winter and early spring. At that time, there was major efforts to improve air quality in the United States with the formation of the Environmental Protection Agency in 1970. The state of Alaska, eastern Siberia, and Canada, however, did not have any major sources of pollution as there was no major industrial centers in these regions. Shaw found that the unique conditions in the Arctic, low water vapor and low mixing, allowed long-range transport of pollutants from central Russia, then the Union of Soviet Socialist Republics, across the pole to Alaska, so explaining the source of this Arctic haze. So summing up Unit 4, we note the following. 1. In the atmosphere, energy is transferred by conduction, convection, and radiation. 2. The overall energy balance of the Earth-atmosphere system is determined by the input of solar radiation in the visible and the output of terrestrial radiation in the infrared. This is called radiative equilibrium. 3. All objects at any temperature above absolute zero emit radiation. 4. The Sun at 6000 Kelvin emits light at about 500 nanometers, while the Earth at 300 Kelvin emits at about 10 microns. 5. Over the year, there is a surplus of energy at low latitudes in the tropics and a deficit of energy at high latitudes near the poles. Energy transfer from the tropics to the poles is carried out by weather systems. 6. Water droplets and ice crystals refract light and create a variety of optical displays. These displays can be used to forecast the weather. 7. Energy balances also drive the diurnal and seasonal cycles in temperature. Diurnal variations driven by the day-night cycle are larger at the surface due to conduction. Diurnal variations are weakened by cloud cover. Seasonal cycles, driven by the Earth's tilt, are larger at higher latitudes. And finally, number 8, the Arctic atmosphere is polluted due to unique conditions that trap pollution from lower latitudes in the polar air mass. Thank you for your attention.